presentation things. I know a number of you have been asking about when the test will be back and all of that. I'm working on it. I really am. I'm going to stay here tonight late and grade until I have to go home. So I'm hoping that I can get a bunch of stuff done. And I will also get some information to you tomorrow about how grading is working. We're trying to get our grade book set up through Canvas to make it work that way because I think it will work better. So I'm just letting you know that we're working on it. I haven't forgotten and I care about you and we'll get there. It's just, it takes a little time. Today, we're going to work on this warm-up problem, although it's going to kind of end up being an all-period problem. We're going to talk about the buggies and marble real quick, and then we'll do a couple more things. I do want to draw your attention to the fact that you have homework tonight. We've had no homework for the last couple nights, so I just want to remind you and get you back into that routine. Regardless of how far we get today, that homework will be valid and worth doing tonight, okay? We're going to come to this warm-up problem in just a moment. Yesterday at the end of the period, you remember we were working on the marble on a ramp problem. And then at the end, after you turned your stuff in, I asked you to write down this chart. And I'm hoping you have done that. And most of you said that you had finished it. But I just want to verify with you that we're all on the same page so that there's no confusion later. No, I didn't know that. Like, yeah, you did, and here it is, right? That's what we're doing right now. So, what's wrong? Oh, yeah. I'll pull it up in just a second. Hold on. So, yeah, homework, here it is real quick. 13, 15, 17, page 74. All right. So, physicists, there's a lot of conversation happening today. I'm going to tell you that my throat is a little bit sore and I cannot talk over you today. So if you need to sit somewhere so that you're not going to talk, then please do that. You can go ahead and move yourself now. Okay? Or if I ask you to move, I just need you to do it. I cannot talk over you today. Okay? And we're also doing some heavy physics stuff that I want to make sure everybody has the opportunity to learn. So that means that you need to be respectful. Even if you don't want to learn it, although you probably do, you need to make sure that you're paying attention or giving other people the opportunity. Okay, so I asked you to write this down, so this should go really quick. But again, I just want to make sure that everybody's got this recorded and in your notes so that you've got it. So the buggy, who can describe for me the motion of the buggy? I'm going to start at this table. Go around. What'd you guys get? Or what did you say?
Positive constant motion.
Positive constant. So you said motion. I'm going to use a little bit more of a technical term there. Can I say velocity? Is that okay? Does that still match what you're thinking, though? Okay, cool. Positive constant velocity. Everybody okay with that? Okay. Doop, 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 doop. There goes the buggy. All right, hold on just a second. So now I want to draw or sketch the position versus time graph for that buggy. We're just going to go kind of around the room here. So let's see. I don't know. Who wants to do that? Olivia, did you guys get a picture for that?
I did.
No, I'm going to ask you. I'm going. I don't want to go every person because that'll take forever. Yeah. It's like you're acting it out. But yeah, it's a straight line, right? With a slope. Yeah. With a positive slope. So something that maybe looks, oops, I was going to do this in red to keep my colors consistent here. These colors are nice. Something like this. Okay. We're going to label our axes just so we have it. So if you did not have this in your notes, do it right now. Okay. All right. My back corner table. Let's see. Jordan, did you guys have something written down for the description of the slope? On the constant positive, she says. I agree. Oops, I wrote the positive first, but it's the same thing, right? Positive constant. I just put my pluses and minuses in parentheses so that you know that it's a thing as opposed to just a line sitting somewhere. That I just wanted to explain that to you in case it was confusing. And then, going back to my back middle table here, like Erica, Anna, somebody got it. What did you guys say for the velocity versus time graph? What does that one look like for you? Perfect. Yeah, it's a straight line. Straight horizontal line. And why is that? Because the positive constant slope tells you the values for the velocity. Positive constant values. How are we doing, team? Are we okay so far? Fantastic. All right. My back bar table over there, we got Drake, AJ, Cole. What'd you guys get for the description of the motion of the marble? Say it again.
It's positive and it's like accelerating.
Ooh, nice. Positive and accelerating. Now, I can't remember because I've got 3 classes doing all kinds of different stuff and I can never quite keep track of where I've had the conversation. Have we defined this term in here yet?
No.
Okay, so let's do that. Many of you probably have heard that term before or have an idea of what it is, but I want to make sure that you actually understand what it means to accelerate. So I'm going to keep poking you a little. Is that okay?
Yeah.
Instead of accelerating, is there another way that you could describe that?
Going faster.
Going faster, right? Increasing velocity or speed, yeah. So accelerating means increasing, decreasing, actually even changing direction, changing velocity over time. But we can all agree that that marble, it started off at a velocity of 0, right? It wasn't going anywhere. We released it from rest, and then as it went down the ramp, it got faster and faster and faster and faster. That's why it was harder to like chase it down when you were marking it with the metronome going. Yeah.
So, would you be able to like calculate accelerating at like with like delta velocity over time?
That's exactly what we're gonna do. Thanks for asking, because I was about to write it down. So acceleration literally means, from a calculation perspective, the change in velocity, delta V, so VF minus VI, right, divided by T. And later this week, we're actually gonna start doing that and start digging in and figuring out the numbers. Right now, though, we're just gonna know that that's what it is. So this is maybe the hardest of these 8 questions. The position versus time graph for the marble rolling down the ramp. Y'all graph this. This is what I asked you to graph in that lab graphing yesterday. Let me ask a question. Was it a straight line?
No.
It wasn't. What kind of a shape did it have? What kind of a shape did it have? It was what? It was a parabola. Something like that. Now, if your data didn't look just like that, that's okay. It's all right. But that's what it should look like. Okay? No judgment if it didn't. Like, that's all good. That's why we're learning together, right? Let's describe that slope. Tell me about that slope. What is that slope doing? Is it staying constant? I'm talking to my table right here. Is the slope in this graph constant? It isn't. What's happening to the slope?
Increasing.
It's getting, oh, that gray you can't see very well, can you? Let me get a different, brighter color. We see how the slope is getting bigger and bigger and bigger? The slope is increasing. Do you notice that it's always positive, though? Hopefully. It is positive and increasing. And then if I go back to my velocity versus time graphs, did you guys sketch a velocity versus time graph for that marble? It looked like that. I like the. I feel like we need to do like an interpretive dance of graphing. I feel like that would be a good thing for all of us, right? Interpretive dance graphing. I think that'd be beautiful. Something like this. Yeah. Awesome. Okay, so you've got that. Now, what I would like you to do, I just wanted to make sure we had that under our belt before we started like actually talking about the warm-up problem. I'm going to go ahead and click back to the warm-up problem. Is that okay with everybody? Yep. All right, fantastic. So it asked you to describe the motion of the frog. It's not really a frog unless it's going really fast. I hadn't really read the graph until last period, so I apologize. Really fast frog. I would like to know what's happening with this frog. It says describe the motion. This is a velocity versus time graph, to be clear. Who can tell me what's happening at the beginning of this story? Go for it, Ad. What you got?
He stopped on a lily pad to eat a fly.
He stopped on a lily pad to eat a fly. I would 100% agree with that if this was a position graph. Does that make sense? But it's not a, right? Would you guys agree if it was a position graph?
Yeah.
That the frog is just hanging out for 2 seconds eating a fly on a lily pad? I 100% agree. But, and this is part of the reason that we do this, right? So now I'm gonna let you take a look at this again. So Ed, what do you think? If it's not sitting still. What's going on for this 2 seconds?
He's going to another lily pad.
He's going to another lily pad, right?
I'm gonna catch it.
Yeah. How fast? How quickly?
4 meters per
4 meters per second. That's kind of a lot, which is why I said, maybe it's probably should be a car or something like that. It's all good. Either way, we can say that from time equals 0 to time equals 2 seconds in both cases. What's that? That's true. They can swim really fast. Thank you. Thanks for saving. I was thinking it wasn't going to work. But yeah, if he's swimming, for sure it could happen, right? He is moving at a constant speed. Okay. And that constant speed is positive. And it has a value because we have actually a number here. 4 meters per second. Bam. How we doing, team? Cool? Fantastic. Now, something different happens at 2 seconds. Sam, do you know what happens at 2 seconds?
Yeah, it starts to like decrease to a stop.
Decrease in
Velocity.
Yeah, absolutely. So from time equals 2 seconds to time equals 4 seconds, he slows down, right? We can also use the A word in order to describe this because a slowdown is still an acceleration. So sometimes people like to use the word deceleration or deacceleration or kind of funky words like that. I'm never going to use that. That's not something that physicists use. We'll just say that the frog has a negative acceleration. And by the time it gets to 4 seconds, I feel like maybe you said this, but I can't remember. How fast is it going?
It stops.
It stopped. Okay, so it stopped. Slows down, negatively accelerates to a stop. Fantastic. We doing okay? Issues or questions right now? Got kind of an image in your head of this swimming frog. It's swimming fast, so I appreciate the swimming part. Yeah? I've got a follow-up question for you. Okay? The follow-up question asks you to draw a position versus time graph and an acceleration versus time graph that match this one, right? That tell the same story. I'm going to give you about 30 seconds by yourself, no talking, no looking, no whatever. I want you to see if you can do it in your notes by yourself, and then I'll give you some time to talk, okay? Go ahead and give it a shot. Friends, so you've got something written on your whiteboard, or maybe you don't, and if you don't, that's okay too. We are going to come back to this. So what I'd like for you to do is to put that whiteboard and marker just kind of to the side, or set it somewhere where it's not going to be distracting. I walked around and gave you all a golden sheet of paper. Okay? What's that? Are you sad that I'm not sure the answer yet?
Yeah.
Oh, we will. We'll get to it, I promise.
Oh, that's
But I want to make sure that you have an opportunity for an informed answer. Okay? So on this golden sheet, I don't know if you've ever noticed, I'm a teacher that I like colored paper. You've probably gathered that. Okay? I know, right? But I use those darker colors like the gold or like the reddish color when it's something that I think you might want to hold on to and refer to when you're studying or when you're working. So this is one of those pieces of paper, okay? So I'm going to give you an opportunity to learn about how these things work to kind of put this all into context so it makes sense. There's going to be a lot of repetition in the next few minutes, and that's okay. The repetition is to help you get it into your brain, okay? So there's nothing bad happening. It's just to get a sense of what's happening here. So I've got 3 sets of graphs, 3 rows, and on each row, we're going to have a position graph, a velocity graph, and an acceleration graph. So if you would like to go ahead, oops, not acceleration there, and label this, that's going to be a position graph. This is going to be a velocity graph, and the third one will be an acceleration graph. And I'm going to go ahead and label all 9 of my graphs. So that top set, again, it goes from left to right, position, velocity, acceleration. We're going to get our heads around what is really going on here. So position, velocity, acceleration. And the way we're going to do that is by looking at 3 distinct scenarios, 3 distinct descriptions of motion and how they compare. What's the same, what's kind of different. So go ahead and label all of those axes so that you've got them. These are just sketches of graphs, okay? And we're going to start with this top set. And my philosophy on learning things that are hard is to start easy, start on a place that we all understand, and then we can work from there, okay? So the first graph that I'm going to show you is not terribly complicated. It looks like this. A position versus time graph that looks like that. At your tables, talk to the people sitting next to you. What is this graph describing? What kind of motion? Or what's going on with the object? Go ahead and talk real quick, just like a super fast.
No, it's not going. It's just
It's not moving.
Right? Yeah. All right. So Dawson, what did you guys come up with over there?
It's not moving.
It's not moving. This object is at rest. Object is at rest. It's not moving. Okay? Pretty unexciting situation, right? Okay? Object is at rest. If the object is at rest, what's its velocity? 0, right? We got that. Okay. Easy? We got that? All right. And I just drew a line right down here. If you can almost not even see it, right? Yeah. So because the object is at rest, I know that the velocity is 0. Now, we said just a few minutes ago that acceleration means change in velocity. So quick question, friends. Is the velocity changing during this story? No, because the velocity is what? 0. So if the velocity is 0 the whole time, that means that the acceleration's got to be what? 0. That's a pretty easy scenario, I think. We can all kind of handle that one. Okay? These little arrows and boxes I'll fill in a few minutes. Just be patient with me, I promise. They're there for a reason. I want to move on right now to a more interesting picture or a more interesting story. Here's story number 2. Are you ready for it? Ready? We're going to go like this. Whoa, that's so cool, right? Maybe not. Maybe that wasn't quite your reaction. At your tables, tell the story of this graph. What's going on in this story? All right, Brianna, what'd you guys come up with? What's increasing? So the object is moving, right? And it's moving at, what did you say? Okay. Yep. So we're coming back here, friends. Coming back all to one group. So we've got an object that is moving at a constant speed. I'm going to use the word velocity because indeed the velocity is constant. Okay. And is the object moving in a positive direction or a negative direction, do you think? Positive direction? What evidence do you have for that? It's in the first quadrant, right? We know that it's going away from the origin in a positive direction. So we can also say that it's got a constant positive velocity. Now I know, because you've done this before, using the displacement versus, or the position versus time graph that looks like this, can you determine what the velocity versus time graph is going to look like? What's it going to look like, friends? Straight line, straight horizontal line, absolutely. Okay, so you know that because we've done this a few times, but I want to talk through exactly why that's true. What is it about this graph that you looked at to determine that this is a straight horizontal line? The slope, right? You've been training for this for a long time. You know this. I'm going to go way back up to the top to this arrow here because that's going to be kind of my master list. So in this little arrow, these arrows are kind of small, but I had to fit them in the picture. So if you write bigger, you might need to like squeeze it some outside the arrow. But in this arrow, this is again in the top left-hand corner, we're going to say that to go from the position graph to the velocity, we're going to look at the slope. Okay. I'm going to say of the position versus time graph. to determine the velocity versus time graph. Okay? It was pretty easy in this first one. In this first one, the slope was, yeah. And in order to do that then, or using that, we could figure out that the values here were 0, right? Because it wasn't moving. So I'm going to write in this little box, I'm going to say that the slope of the position versus time graph determines the values of the velocity versus time graph. So the keywords here are that the slope of the position versus time graph determines the values of the velocity versus time graph. Because the slope here was 0 in this position versus time graph, the values here are 0. How are we doing? Doing okay? I'm going to go down to the second story now and just do exactly what we said. The slope here is positive and constant, which means that the values here must be positive and constant. Do you see the nice symmetry here? The slope here is the same as the values here. Okay. Why is that? I'm going to fill in this little bubble or this little cloud. I'm going to say that we're going to remember that velocity is change in position over time. That's why this is true. How are we doing? Are we okay? Okay. So now, quick question for you. If the velocity here is constant, are we going to be accelerating?
No.
No. So what's the acceleration value going to be here?
0.
0. How are we doing? What's up?
A little off topic, but would we have arrows at the end of our lines? Because
Arrows here.
because wouldn't it technically be going?
I mean, you don't know if it's going to continue in that direction or not.
Okay.
It might do something different. So I would say no. No. I mean, I wouldn't count it wrong if you did, but I generally don't. Does that make sense? Yeah. Okay. All right. We're going to go down to story number 3. Before we do that, though, hey, I have a question. Have you seen this story before? Did we do a lab with this one? Yeah. What was that? Which lab was this?
Bucket line.
It was the buggy lab. Yeah. That's just kind of a nice reminder. Did we do a lab for the top one? That would be a really unexciting lab. Do you agree?
Yeah.
Watch this thing sitting here like that. No, yeah, we didn't do it. But the middle one is the buggy lab. Here's number 3. This is scenario number 3. You may be able to predict what's going to happen. Maybe not. I don't know. We'll see. Looks like this. Were you going to guess that? Maybe, maybe not. Tell me a story. What's going on in this one? Talk to your table real quick. Do you have an idea of what's going on in this one? You guys got it? Yeah? What'd you say, Haley? What's happening? It's accelerating. So you have an object that's accelerating. That's exciting. It means you have an object that's speeding up, right? It is, in fact, speeding up in this case and moving away from the origin. In a positive direction. Are you guys doing an interpretive dance of this? Is that what's happening back there?
Yeah.
Yeah, I mean, it should be, because why not, right? But yeah, I just want to make sure we're good. All right. So, we've done this before, but I want to make sure that we can interpret from what we've done earlier in this page. I'm going to look way back up here. Remind you that we're going to look at the slope of the position versus time graph to determine the velocity versus time, right? So let's go ahead and look and see what happens. Again, to the slope here. So remember, the slope is like that tangent line. Tell me about the slope of this curve. What can you tell me? The slope is increasing. It is. And I heard another description. What'd you say? Somebody? It's always positive. Do you notice this? It's always positive. That means it's going up, 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 right? So we got a positive increasing slope. So we can follow the instructions. And if our slopes are positive and increasing here, what does that mean about our values for the velocity versus time graph? Increasing and positive. Yeah. We can remind ourselves that that looks just like this. Okay? So now we have to think a little bit again. Oh no. Except we can do that. Is the object, oh, it says that it's accelerating. I was about to ask if it was accelerating, but the answer is what? Yes. Accelerating means what again?
Increasing change in velocity over time.
Changing in velocity over time. I'm going to write that down here. Again, just so that I've got it in my brain so that I know it. The more you write it, the better it's going to stick, right? The acceleration is change in velocity over time. And oh my gosh, it is absolutely changing velocity, isn't it? Yeah. So we can use that information to figure out our acceleration graph. I'm going to go way back to the top again and write down our rule up in this top one here, okay? The rule is going to be that we're going to, I mean, this might not surprise you. Maybe it will, I don't know. We're going to look at the slope. We're going to look at the slope of the velocity versus time graph to determine the acceleration versus time. Okay? And then in that box, again, I'm on the very top right, okay? The slope of the velocity versus time determines the values of the acceleration versus time graph. Okay? There's really nice symmetry here. Oh, I do not need to open Word right now. Thank you. The slope determines the values. You may feel like you've just written that, and it's because you did. This box here and this box here are almost identical, aren't they? Okay? They're very, very similar. So let's figure out going from velocity to acceleration in this one. The slope of this graph is what? 0. Oops. And if the slope is 0 here, that means the values here need to be 0, right? That's why it is what it is. Okay. I'm going to go down one to the middle story. Is that okay? Sorry. Slope values. Same here. Let's do it. So the slope in this case, what is the slope for this one? It's still 0. Okay, well, we can do that. Slope equals 0. That just means that the values here are 0. Not a surprise. That's what we had graphed before. But now we have a reason for it. Okay? Here comes the last one. Tell me about the slope here. It's positive, isn't it? Is it increasing, decreasing, or constant?
Constant.
The slope is constant. Do you see this? The values are increasing, and it gets a little bit confusing, which is why we have to think about it carefully. When we're talking about the slope here, the slope is positive, and the slope is constant. Yeah. So the slope is positive and constant, which means that here the values must be positive and constant. How are we doing? We okay? So we can now graph that. Positive, constant. I can do that. Bam. Have you seen an example of what we drew in this last one? A displacement or a position versus time graph that looks like this? Yeah. This is the marble on the ramp. Indeed. What I would like you to do right now is to take all of this newfound knowledge, okay, and apply it to that warm-up problem that we did before. Okay? So now that you know all of this stuff, talk to each other for another moment about the position graph and the acceleration graph. Friends, I will tell you that the acceleration graph is easier, so I would start there. And I will tell you that the position versus time graph is a thinker. Okay? You're going to have to do some thinking on that to see if you can get it. But I think you can try, and we'll get there. We'll get there. Okay? Take a couple minutes and have that conversation. If you need to change what's on your whiteboard, do that. We'll come together in just a minute or two. Go. Chance to go through it. So let's take a look here. As I said, the acceleration versus time graph is probably the easier one to do, so let's start with that one. Okay? And we've already talked about what happened. This is all building to this answer, right? So at the beginning, let's look at just those first 2 seconds. For those first 2 seconds, I'm just going to give myself 4 seconds over here. Oh, it's frozen, so you can't see that. Sorry. There you go. Bam. Thank you for letting me know. I appreciate it. For the first 2 seconds, we need to look at the slope of the velocity graph to find the acceleration. What's the slope here?
0.
It's 0, right? The slope is 0. Oops, I was going to write that in a different, that's okay. Slope equals 0. And if the slope is 0, what does that mean the acceleration is? It's 0, right? How many of you guys got that part? First 2 seconds? Awesome. Good for you. If you didn't, I'm hoping that through talking it through just there, that made sense to you. Will you have to do something like this on a quiz or a test? Yeah. Yeah, so make sure you're with me. If it's not making sense, don't turn your brains off, friends. I need you to understand this. I want you to get it. Okay, so we looked at the slope for the velocity versus time graph to get the acceleration for the first 2 seconds. We're going to do the same thing for the second 2. All right? We need to find the slope. Can you find the slope of this line? How do you find the slope of a line? Rise over run. Change in y. What's the change in y? -4, right? What's the change in x? What is it? 2? -4 divided by 2. I can do that in my head. What is it? -2. The units are meters per second squared. We'll talk about that later. Don't worry about that part. That's not a huge deal. But that's what it's going to be. So we're going to be down here at -2. Bam, bam. -2. Okay? That is the corresponding acceleration versus time graph. You guys with me? Is that okay? Okay. Let's do this one. The position one's a little bit more challenging, but I know that you can do it. We have to work backwards. Remember that these values here now tell us the slope on the position graph. What is the value of the velocity versus time graph over the first 2 seconds? What is the value here? 4? Yeah. The value here is 4 meters per second, which means that the slope over the first 2 seconds, 1, 2, is going to be 4. I'm just going to sketch it. So it's going to be a straight line. This is a constant positive value. So this is going to have a constant positive slope. This is where it gets tricky. Tell me about the values for this here from 2 to 4 seconds. What do the values do? They decrease. And are they positive or negative values? Help us out, friends. I need more than just 2 people to talk to me. Are these positive or negative values?
Positive.
They're positive, and they're getting smaller, right? Positive values that are getting closer, decreasing, closer and closer to 0. This is what it's going to look like. It's going to look like that. What? That's weird. It's totally weird. I will tell you that everything up to here is totally valid for a quiz or a test. This part I would not put on a quiz or a test, okay? Because that I feel like is pretty tough. But just to show you, right? You've got a positive value for the slope, and that slope is getting closer and closer to 0, which is exactly what Sam told me earlier was going to happen, right? It slows down. It has a negative acceleration. It gets closer to a stop, okay? It's kind of weird, but it's doable. We've got a question?
Why wouldn't you put down?
Because I'm still moving away from my origin. So my velocity is still positive, which means I'm still going away from the origin. It's weird. This is like the first steps into weirdness, right? But yes, I totally, so it would be,
Going back down to 0 though?
yeah, so watch. I'm gonna do it. Are you ready? You watching? Everybody watch. So I'm not gonna walk at 4 meters per second because I would run out the door really fast. But I'm gonna walk at a fast speed, and then I'm gonna slow down. You with me there? So I walked at a fast speed, and then I slowed down. But I'm still going this way. So this would be like a football player, right? That's running, getting towards the end, the goal line, right? You're gonna run as fast as you can, but once you hit the goal line, do you need to stop? Probably at some point. And so you're gonna slow down to 0, but you're not gonna turn backwards.
We're not winning.
That wouldn't work, right? That would not help. Yeah.
Why would the slope get steeper as you start to slow down?
Say that one more time.
Why would the slope get steeper as you start to slow down?
The slope gets less steep. So it's really steep here, and then it gets less and less and less steep. It gets closer and closer to 0. Does that make sense? It's weird. It looks funny. Yeah. Yes, it should. You're right. Yes, that's a good call. Yes. All right, my friends, I need you to listen for 5 seconds because the bell's going to ring in just a moment. Shh. On that green sheet that I handed you, guys, I'm going to hold you after the bell if you can't listen. I can't yell over you, so please listen. On the green sheet that I just gave you, I want you to work on a couple of questions to see how they go and so that we can have something to talk about tomorrow. On the front, on question 1, you're going to work on A, B, and D. Okay? What's that? Oh, well then that's good. And then on number 2, I want you to work on all of them. Give them a shot. Okay? So work on that. Work on your homework. Come ready to do some more graphing tomorrow, okay? I will put the homework back up. Yes. And there you go. Friends, thank you very much for your hard work today. I hope you have a fantastic rest of your Wednesday. Luke, you are absolutely right, by the way. Yes.